Yeah, we will discuss the doubts from the major test 6 today. Let's start with that, in fact. So let's start with the JEE Advanced paper. So just give me a moment, I will share the paper. In the meantime, you can start telling me the questions you have doubts in. Okay, so let's go through the section 1 of the advanced paper. So anyone has a doubt in the first two questions, anything? Please go through question number 1 and 2 and let me know if there's any doubt. Okay, Samarth has a doubt in question 2. Let's discuss. Okay. So with what minimum speed v must a small ball be pushed inside from a height h so that it may reach the top of the tube? Okay. All right. So this situation, when you have a tube like this, which is smooth, the condition for the object to reach the top is that whatever speed you give over here, when it reaches the top, it should have v greater than equal to 0 to reach, let's say, that point A. Okay. So from this point, let's say B to A, you apply conservation of mechanical energy. Change in kinetic energy plus change in gravitational potential energy should be 0 because there is no friction. Okay. And normal reaction does not do any work. So half mv square minus u square plus mg, अभी ये height कितना हो जाएगा? From B to A, this height will be 2r minus h. Should be equal to 0. Okay, Shikhar will discuss that also. Okay. So from this, you can now see that you'll get b square is equal to u square minus 2g into 2r minus h, and this should be greater than equal to 0. It means u should be greater than equal to square root of 2g into 2r minus h. So the minimum condition will come from the equality. Is it clear, Samarth? Let's check out the answer. Okay. Should be the same. Yeah, appears there's a misprint here. It should not be 5R. This should be 2R. Yeah, there should be a correction in this. This should be square root of 2G into 2R minus H. Okay, this is the correct answer. Okay, I will get this corrected. Should get bonus marks for this then because none of the options are correct. Okay, let's look at question number 1. Shikhar has a doubt in it. So particle of mass m is attached to a string of length L in a smooth plane inclined at an angle E. This should be alpha actually with the horizontal. For the particle to reach the highest point, its velocity at the lowest point. So this is like an adaptation of the vertical circular motion. ऐसे प्लेन में, ऐसे स्मूथ प्लेन में वो is doing circular motion. Understood, Nashika? So the force that is acting along this direction is g sine alpha, mg sine alpha. So if you give it a speed, now at that bottom point, if you give it a speed v naught, then you assume that by the time it reaches the highest point, its speed should become v. So now you can see from the bottom point to the highest point, what is the height difference? The height difference will become 2r sine alpha from the bottommost point to the highest point. You understand me? Because this distance will be 2r. So the height difference will be 2r sine alpha. Okay. So you'll have half mv square minus v naught square minus or plus mg into 2r sine alpha is equal to 0. So at the topmost point, v square is equal to v naught square minus 2gr sine alpha instead of 2gr. Okay, so this is one equation. It's coming from work energy. Now at the topmost point, the tension should be greater than equal to 0. So how we'll understand about the tension? The force acting along this direction will be mg sine alpha. It's like this. So if tension is just about equal to 0, or we can write the equation for tension, tension plus mg sine alpha, that should be equal to mv square by r. This equation is clear, Shikhar? Mg cos alpha is balanced by normal reaction. Okay, very good. So then what is your equation for T to be greater than equal to 0? Implies that mv square by r should be greater than equal to mg sine alpha. Okay, so this thing, so v square, so this is your second equation. Now you substitute the condition of the second equation in the first equation. Okay, so what is the relation you will get? That this thing v naught square minus 2gr sine alpha should be greater than equal to this thing. Oh, wait a minute. There is another 2 somewhere. Miss this out. This condition will give you 4 here. Let's make a correction. This should be 4 here. From this equation, when you solve now, 4gr. So this will be V naught square minus 4 GR sine alpha. Okay, this should be greater than equal to, from this, GR sine alpha. So V naught should be greater than equal to root 5 GR sine alpha. In a vertical situation, it becomes root 5 GR. So here it's on the inclined plane. So G is replaced with G sine alpha. And R is L, basically, the length. So that's why this option is correct. How many people are here who are still not given the major test? How many people are there here apart from Kavindra who are still not given the major test? Okay. So Kavindra and Suyash, two people have not given the major test. Anyone else? When are you people planning to give the test? Kavindra and Suyash, when are you giving the test? Okay. Okay. So we will postpone the discussion of the major test to next week then. We will postpone the discussion of the major test to next week. We'll continue to heat and thermodynamics today also, because there are still students who have not given the test. So because of KVPY preparation, there are still some students who have not given the major test 6. So we will postpone the discussion of major test 6 till next week, because they're giving it on Sunday. So let's continue ahead with heat and thermodynamics. So today we will start with the next section of this, calorimetry. Okay, so calorimetry is the subject that has to do with the relationship of heat versus temperature for a given material. Okay, so if you look at the relationship between heat supplied versus temperature for a given body or material, then what we see is that there is a linear relationship. Suppose we plot a graph between Q, which is the amount of heat supplied, in joules, versus temperature, Kelvin or degree C, whatever. Yeah, principle of calorimetry has to do with that. That's correct, Piyush. Okay. So the relationship between heat and temperature for a given material is linear. Say the temperature starts from some non-zero value. Now, as we supply heat, the temperature increases proportionately. Or what we'll do here is we will take the relationship like this, that we keep heat as the control variable versus temperature is what we are measuring. Okay, so we are seeing temperature as a function of the amount of heat supplied. Suppose we are looking at that, then what we'll see is that as we supply more and more heat, the temperature increases linearly. Okay. Suppose the material to which we are supplying the heat is solid. Okay, so this will happen up to a certain temperature, and that temperature is called the melting point. Now, the moment we reach the melting point, what happens is that we supply heat, but temperature doesn't rise. So at this stage, what happens is the process that occurs is melting. So we supply heat, but the temperature remains constant till all the material melts, and now we have liquid. So once we have liquid, once the melting process is complete, again with heat supplied, the temperature rises till we reach another situation where another state change starts to occur. And that state change is boiling. Okay. So this is in the liquid phase. Now once it reaches boiling point, again with heat supplied, first vaporization occurs. And then again the temperature starts to rise. So for a solid material, if temperature is less than melting point, the amount of heat supplied is directly proportional to the temperature change, or the temperature change is directly proportional to the heat supplied. Okay. Now, in this relationship between the two, when we look at this is a constant, where this constant is called the heat capacity for the given solid body. So heat capacity is basically what? It is Q upon delta T. Heat capacity is defined as the heat supplied per degree change in temperature. Okay, we will talk about specific heat capacity also, but first let's understand what is heat capacity. So it is SI unit is joules per Kelvin. Okay. We can also express it in joules per degree C, or also in calories per degree C. Okay. We will talk about the unit of heat being 1 calorie also. The SI unit of heat is joule, but there is also a common unit calorie, which is equal to 4.2 joules approximately, 4.18 joules more precisely. So calorie has a special significance, which we'll talk about when we talk about a specific heat capacity concept. Okay. So just note down the definition of heat capacity first, and this graph. Okay, now the next important thing is that if the solid is what we call a homogeneous solid or an isotropic solid, that is, it's made of one material. If the solid is an isotropic material, that means it is homogeneous. It's not a mixture. Then the heat capacity is directly proportional to mass, and it is given by the relation m into small s, where small s is called the specific heat capacity, okay, of the material of the solid body. Whatever homogeneous material or isotropic material the solid body is made with, that material has a specific property called the specific heat capacity. So Q is equal to C delta T becomes M into S into delta T for a isotropic body or material. So S is Q upon M delta T. So specific heat capacity is heat supplied per unit mass per degree change in temperature. So this is the definition of specific heat capacity. So S is measured in joules per kilogram Kelvin. That is the SI unit. But we sometimes also measure it in joules per gram degree C or calories per gram degree C. Okay. Just write it down, Shikhar. It's self-explanatory. Okay. What we observed from the experimental analysis is that when you take a solid body and you heat it, the amount of heat supplied versus temperature change, it's a linear relationship. So further, if that solid body is made of a homogeneous species, like it's just one material, like it's one metal, or it is wood, or it is plastic, or whatever it is, but there's no mixture of materials, then the heat capacity itself will be directly proportional to the total mass of the material. And that proportionality constant is called the specific heat capacity. It's self-explanatory. Just make a note of it, you'll understand. So at the molecular level, the explanation of this is that, the temperature is directly proportional to the average vibrational kinetic energy of solid molecules. So when we are supplying heat, the vibrational kinetic energy of the molecules is increasing proportionately. So as that increases, the temperature increases proportionately. So the amount of heat supplied, it should be directly proportional to the increase in kinetic energy of the molecules. So it's directly proportional to the temperature change. Now the constant of proportionality, if we have a homogeneous solid body or an isotropic solid material, then the relationship between Q versus delta T, the constant of proportionality will be directly proportional to mass also. So it is M into some constant into delta T. So that constant is the specific heat capacity. It is heat supplied per unit mass per degree change in temperature. So that becomes a definition of specific heat capacity, that if I have 1 unit of mass of that material and I want to change its temperature by 1 degree C, if I want to increase its temperature by 1 degree C, I have to supply exactly that much amount of heat. Or if I want to decrease, I have to withdraw that much amount of heat. So I have to absorb that much amount of heat from it. So it's a very simple definition. Okay. Next, we will see that when a solid material is at a particular temperature, called its melting point, then heat supplied Q that results in melting, that is state change, okay, to liquid, and the temperature remains constant with heat supplied until the melting process is completed. That is, all the solid has converted to liquid. Okay, so we look at temperature versus heat supplied. Now we are supplying heat, but the moment we reach the melting point, the temperature becomes stable for heat supplied till all the solid is converted to liquid. The temperature will start to rise again only when we have 100% liquid from the solid. So the amount of heat supplied for the melting process is directly proportional to mass. And this is the amount of heat supplied for melting at the temperature equal to the melting point. So that constant of proportionality is called latent heat of fusion. Heat per unit mass for melting process. So the quantity L is called latent heat of fusion in joules per kilogram or joules per gram or calories per gram. So latent heat of fusion is the heat required per unit mass of solid to be melted at the melting point. Okay, just note this down first. I'll take you back to the last slide. Yeah, Piyush, you can express in calorie per kg also. Any combination of Q versus mass is fine. But I'm saying generally we don't express that way. We express in calories per gram. But the SI unit is joule per kg. Okay. So I'll just give you an example here. The specific heat capacity of ice is about 0.6 calories per gram. Okay. Or that is the same thing as 0.6 into 4.2 joules per gram. Or that is the same thing as 0.6 into 4.2 into 10 raised power 3 joules per kg. This is the specific heat capacity of ice. Later we'll see that specific heat capacity of water is equal to 1 calorie per this is per degree C. So that is where the definition of 1 calorie comes actually. 1 calorie is defined as the specific heat capacity, or 1 calorie of heat equals to 4.18 or approximately 4.2 joules. 1 calorie is defined as the heat needed to raise the temperature of 1 gram of water by 1 degree C or 1 Kelvin. So that is the significance of 1 calorie of heat. Yeah, sure, Piyush. Okay. So the inverse relation of this, what you are saying is correct, that 1 calorie is 4.2 joules, means the reverse of this, that 1 joule is equivalent to 1 upon 4.18 calories, or that is equal to approximately 0.24 calories. Okay. So this is the interconversion between joule and calorie. Okay. So next up, the definition of latent heat of fusion. So hope this is clear. So here we'll take the example of ice. latent heat of fusion of ice in the non-SI unit is 80 calories per gram. Okay, so that becomes 80 into 4.2 joules per gram. So that is the same thing as 80 into 4.2 into 10 raised power 3 joules per kg. So this is the SI unit, and in this unit it becomes approximately 3.36 into 10 raised power 5 joules per kg. You don't have to memorize these values. They'll be given when we are solving numerical questions. But for ice and water and all this, is quite common in questions. So okay, so once the melting process is completed by supplying the required amount of heat, that is m into L, at the melting point, you have 100% liquid. So for liquid at a temperature which is greater than equal to the melting point, okay, again Q is directly proportional to temperature change, okay, and ms delta T, where S is the specific heat capacity of the liquid now. Okay. So the same chemical species when in solid form will have a different specific heat capacity compared to the when it is in liquid form. So as you have seen that specific heat capacity of ice was approximately 0.6 calorie per gram degree C, but specific heat capacity of water is greater. It's 1 calorie per gram degree C. Okay. Then you reach the process of melting. So again, if you're looking at heat versus, or rather temperature versus heat, now you're in the liquid phase. Then you reach what is called the boiling point. So once again, there is state change that happens. And then in your vapor form, again, the temperature rises. So this process is boiling. So at T equal to boiling point, Q becomes equal to M into L of vaporization. It's called latent heat of vaporization. So heat supplied per unit mass vaporization at boiling point. So for latent heat of vaporization of steam, it is approximately 540 calories per gram, which is equal to 540 into 4.18 into 10 raised power 3 in joules per kg. So that becomes this much. Yes, Viraj, that's correct. For latent heat, the SI unit is joules per kg, but the common unit is calorie per gram. Okay, and of course, once for any gas or vapor at temperature greater than equal to the boiling point, Q is again ms delta T. But sometimes for gas, we also express this in terms of NC delta T, where C is called the molar specific heat capacity and N is number of moles. And we will discuss about this in the later chapter of thermodynamics, the first law of thermodynamics. We should be coming up very soon, this chapter. Okay, now we come to the principle of calorimetry. Okay. And that is like this, that if we have a thermally insulated environment, like a thermal flask, so this is thermally insulated container. That means there is zero heat exchange across the walls of the container. Okay. Then inside this, if we put any two different materials, okay, at two different temperatures, then heat exchange occurs between materials at different temperatures. Okay, such that heat flows from higher temperature material to lower temperature material until what happens? Until there is thermal equilibrium established. That is, the temperature becomes uniform. Okay. So thermal equilibrium means uniform temperature. So this heat exchange happens in such a way the heat lost is equal to the heat gained. So this is called the principle of calorimetry. Heat lost by the materials which are cooling, and heat gained is by the materials that are heating. So this particular equation here, this is called the principle of calorimetry. Remember, this heat exchange is happening in a thermally insulated environment. So there's no heat exchange between the inside and the outside. So in that situation, inside the thermally insulated vessel, any loss of heat by a material which is cooling down will be equal to the total gain of heat by the materials which are heating up. So let's look at a very simple example of this. So basically, a calorimeter is basically nothing but an apparatus to perform calorimetric experiments. So the calorimeter is basically a thermally insulated vessel. Okay. Ideally, it is a double-walled vacuum-sealed vessel. Okay, I'll take you back to the previous section. Finish writing this down. Okay, so let's look at that particular question. So what we've done is inside a calorimeter, which is that vacuum sealed double walled kind of vessel. So there's no heat exchange. We have a certain amount of water. So there is 200 grams of water at 5 degrees C. Specific heat capacity of water is given to us as 1 calorie per gram degree C. That's the same thing as 4,200 approximately joules per kilogram Kelvin. Now a metallic block at a temperature of 80 degrees C, mass of 50 grams, and specific heat capacity of the metal is 0.2 calories per gram degree C is introduced. So we want to find the final equilibrium temperature, thermal equilibrium temperature after a long time. Because if you allow that metallic block to sit in the water for a long time, assuming there is no heat exchange with the outside, okay, because this is an insulated vessel. So we have to find out what will be the temperature after a sufficiently long time when equilibrium is established. So heat will flow from the metallic block to water. So the water will heat up from 5 degrees C, the metal block will cool down from 80 degrees C till the heat exchange stops. So when the heat exchange stops, the whole mixture of metal and water will be at one uniform temperature. So that uniform temperature you have to find out. Okay, so how much the final temperature is coming out to be? So most people are getting different answers. Let me check out. Okay, so see here, what is happening initially, you have M1 equal to 200 grams at T1 equal to 5 degrees C for water. Specific heat capacity of water is 1 calorie per gram degree C, plus you have a mass of 50 grams at a temperature of 80 degrees C of metal, which has specific heat capacity of 0.2 calories per gram degree C. So now let's say the final temperature, final equilibrium temperature is T. So obviously T is going to be greater than 0 but less than 80. So the heat lost by the metal will be equal to the heat gained or absorbed by water. The heat lost by metal will be equal to M2 into specific heat capacity of metal into T2 minus T. And the heat gained by water will be M1 into specific heat capacity of water into T minus T1. So this is our equation. 50 grams into 0.2 into 80 minus whatever final temperature is equal to 200 grams into 1 into whatever final temperature minus 5. So this equation has to be solved. Oh, sorry, 60 by 7. Yeah, correct. तो इंक्रीज ही तो कर रहा है ना बेटा. 5 डिग्री सी से 8 डिग्री सी इंक्रीज ही तो कर रहा है 8.6 डिग्री सी, 8.5, 8.6 something in that region. Yes, it is increasing, na? 5 to 8.6, it's increasing. Water's temperature is increasing, the metal's temperature is decreasing. Okay, so this is clear, I hope. Okay, let's do another question now. Now in calorimetry, when there is state change involved, then the question becomes a little bit more complicated. So for example, we have, let us say, 100 grams of ice at minus 10 degrees C mixed with 500 grams of water at 50 degrees C inside an insulated vessel. Find the equilibrium temperature. So here, given that specific heat capacity of water is 1 calorie per gram degree C, specific heat capacity of ice is given in this particular question as 0.5 calorie per gram degree C, and latent heat of fusion of ice is given as 80 calories per gram. So just note down the data in the question. We'll discuss how to solve this. Okay, so let's see here. What we have to do is there are two possibilities. Okay, one possibility is that all the ice melts. Okay, and final temperature is greater than equal to 0 degrees C. Whereas the other possibility is that there isn't sufficient heat available to make all the ice melt. So 100% of ice does not melt. Okay, and the final temperature remains 0 degrees C. So at 0 degrees C, we have a mixture of water and ice. So first thing we have to understand that which of these two cases is happening. Okay, so for that this data becomes important. We have 100 grams of ice at -10 and 500 grams of water at 50 degrees C. Okay, so what we will do is we will compare two things. One, let's say delta Q1, the amount of heat absorbed by all of the ice to melt. So that delta Q1 will be equal to mass of ice into specific heat capacity of ice into 0 minus initial temperature of ice was how much? -10 degrees C. Plus mass of ice into latent heat of ice. So we had 100 grams of ice at -10 degrees C. So this is 100 into 0.5 into 10 plus 100 into 80 . So we need 8,500 calories of heat to melt all the ice. This is the heat required all the ice. Now probably what we'll see is that much heat is not available to us. Just check out, but my suspicion is that we don't have that much heat available to us, because what is the maximum heat that is available? 500 grams of water at 50 degrees C. So now delta Q2 is the heat given off or the heat supplied when 500 grams of water at T2 equal to, what was it now, 50 degrees C. Okay. 50 degrees C cools to 0 degrees C. So this delta Q2 is 500 grams into specific heat capacity of water into 50. Oh, so we do have. Sorry, we do have enough heat for. So since delta Q2 is greater than delta Q1, that means 100% of ice will melt. And our final temperature will be greater than 0 degrees C. So now we will calculate this final temperature by heat gained by ice equal to heat lost by the water. So the heat gained by the ice is going to be M1 into specific heat capacity of ice into this, okay, plus M1 into latent heat of ice plus M1 into specific heat capacity of water into T minus 0. Okay, so that is 100 grams of ice, which are first coming to 0 degrees C, plus 100 grams of ice, which are melting, okay, plus 100 grams of ice melted into water is rising to a temperature T. This should be equal to, on the other side, into 50 minus T. So this one's temperature is not dropping to 0, it's dropping to some T which is greater than 0 now. So this should be equal to 500 grams of water. So 8500 plus 100 T should be equal to, on the other side, 25,000 minus 500 T. So as you can see, the final temperature will become 25,000 minus 8,500 divided by 100 plus 500. So that is 250 minus 85 divided by 6. This is the temperature that I am getting. You can check out my solution. This 100 T, na? See what is happening. I'll explain. What is happening to the ice here? The 100 grams of ice, first the temperature is going from minus 10 degrees C to 0 degrees C. Then it is melting, and then that 100 grams of water is going from 0 degrees C to the final temperature T degrees C. So this all heat is absorbed by us. So that is why there is this term here. Okay, good. Yeah, Prachi, so what is happening here? Finally, we are solving this, okay, that the heat gained by ice is equal to the heat lost by water. So what is happening? Water, 500 grams at 50 degrees C is cooling down to T, where T is something greater than 0 but less than 50. So therefore the heat liberated by water in the cooling down is this much. Whereas what is happening to the ice, 100 grams of ice, which was at minus 10 degrees C, that is finally converting to water at T. So it is going through the process of first cooling down from minus 10 to 0, then melting, and then that water which is formed, 100 grams of water, by melting the 100 grams of ice, that one's temperature is rising from 0 to T. So this is the total heat. First the ice is heating up from minus 10 to 0, then it is melting, then finally the water formed is its temperature is rising from 0 to T. So that is the total heat which is gained by the ice to become 100 grams of water at T degrees C. That should be equal to the heat lost by the steam, by the water on the other side to cool down from 50 degrees C to T. Okay. So this is the complete explanation of this. Okay, let's do one more example. So again, inside an insulated vessel, okay, let's say 10 grams of ice at 0 degrees C plus 4 grams of steam at 100 degrees C are mixed. Okay. Now given to us that latent heat of ice is 80 calories per gram. Okay. Latent heat of steam is 540 calories per gram, and specific heat capacity of water is 1 calorie per gram degree C. So again, find the final temperature. Find the temperature at equilibrium. So just try out this question while you're noting this down. Okay, let's understand the solution of this. So here, see, what is happening is that to condense all the steam, how much heat you need to absorb. So let's see, delta Q1 heat absorbed when 4 grams of steam is condensed. So that is equal to how much? 4 into 540. So that's how much now? 2160, right? Calories. And delta Q2 is the heat absorbed by 10 grams of ice to melt and rise to 100 degrees C. So that will be 10 into 80 for the melting, and then plus 10 into 1 into 100. So it is 800 plus 1000. So it's only 1800 calories. So you can see that in order to make 4 grams condense, you need to absorb this much heat. But how much capacity you actually have to absorb? Only this much. So delta Q1 is greater than delta Q2. That means 100% of steam will not get condensed. Okay. And final temperature will be 100 degrees C with only X grams of steam condensing. Okay. Where that X will be such that X into latent heat of steam will be equal to this delta Q2 we calculated. So X into 540 will be equal to this 1800 calories. So only 3.33 grams of steam will condense. Okay, so this is the final solution of this. So the final temperature will be 100 degrees C. Okay. And only 3.33 grams of steam condenses. Out of the 4 grams of steam that we had, only this much will condense. Okay, so that was the conclusion of this question. So this is the chapter of calorimetry. It's a very small and easy chapter, as you can see. Only 2 definitions, latent heat and specific heat capacity. And the method of calculation is the important thing when you're doing these calorimetric calculations, that heat lost is equal to heat gained. So next up, the next chapter we'll discuss on our next lecture this week will be kinetic theory of gases. Okay, so this is an important chapter and it will lead into thermodynamics after that. It will lead into first law of thermodynamics. So this has quite a bit of weightage in JEE section that we are coming into now. Yes, calorimetry is done. As I told you, this is all there is to calorimetry. Okay, so that's it for today, people. Thanks for attending and wish you all the best.